So what we'll do today is try to finish off this chapter 4 on material behavior that we've been talking about, and get into actually trying to solve some problems in structural mechanics. We've been building towards this all semester with lot and lots of math, but we essentially want to be able to now get into a position where we can actually solve for the unknown deformation map. So given a structure, boundary conditions, material properties, we want to find the map. That's essentially the problem for structural mechanics. So before we do that, very quick recap of this material behavior that we had been talking about. I mentioned last time that in general, for the class of materials that we said for hyperelastic materials, we have a strain energy density function at each and every material point that describes how strain energy is stored at that point as the material goes through deformation. And we said that that led to a lot of constants, 81, then down to 36 and 21 constants. And then we made this assumption of isotropy, where we said that if we express the strain energy density function in terms of its three primary invariants, then we are down to essentially three scalar material properties for a general isotropic hyperelastic material. And we further restricted it to linear isotropic hyperelastic, and immediately linear means that the strain energy function has to be quadratic, and therefore it boiled down to two material properties. And last time we went through this exercise of how do we find these two material properties. We could conduct a uniaxial tension test that gives us Young's modulus. Young's modulus, that's a ratio of the applied traction on the bar with the elongation in that direction, and the Poisson's ratio, that's lateral contraction with respect to axial elongation. And another test we talked about was the triaxial test, which gave us material parameters, bulk modulus, and I think we were about at this point last time when we were discussing about these material properties. So we went through these bunch of definitions for this bulk modulus. We defined something called the equivalent pressure in a sample, or actually if you go by the sign convention, that this is equivalent suction, and dilation. Dilation is the ratio of the change of volume over the original volume at a particular point in the material. It's not for the entire sample. It could be, we do assume a uniform state of deformation in the sample, but in general, dilation can be different from point to point. And that allowed us to write the equivalent pressure in terms of the dilation. So at a point, if you know the dilation, then bulk modulus is what relates the equivalent pressure to the dilation. And then since we need, so there are these pairs of material properties that we are talking about. The first pair that we talked about was the Lamé parameters, lambda and mu. Two parameters to define a linear isotropic hyperelastic material model. Then we also, with the one-dimensional or in the uniaxial test, we defined Young's modulus and Poisson's ratio. That's a pair of material properties. In the same way, for this triaxial test, people often talk about mu, or which is the same as the shear modulus, G, that some of you might be used to. And this is the way that we define the shear modulus. So there is, if we know the stress state, this was the stress state. We said sigma 1 in E11, sigma 2 and sigma 2 in E22 and E33. So we can define a deviatoric component of stress, which is often represented as S prime. That would be the original stress, state of stress at a point, minus 1/3 trace identity. So this is a very common definition for deviatoric tensors in general. This is a stress tensor, so deviatoric stress is that tensor minus 1/3 trace of that tensor times identity. And for this particular state of stress, we already defined trace 1/3 trace of stress as the effective or the equivalent pressure. So S minus sigma I, that's the deviatoric stress. And um, there is the other part, which actually I should point out here, is this 1/3 trace of stress times identity. This is called the volumetric part or volumetric stress. So volumetric stress plus deviatoric stress give you back the original state of stress. Okay. This, all we have done is divided the state of stress into two parts, deviatoric and volumetric parts. The deviatoric part, again, by using the Hooke's model, doing some algebra, we can show is equal to 2 mu times strain minus 1/3 trace of strain identity, which is just the deviatoric strain. And which means that stress, deviatoric stress, is equal to 2 mu times deviatoric strain. And that's a relationship that we combine often with the bulk modulus and shear modulus to define a hyperelastic material. So, so the stress is equal to that definition of the deviatoric strain, which can be written as the bulk modulus times volumetric strain, which essentially is dilation times identity, plus 2 mu deviatoric strain. Okay, so we have these three pairs of material properties now: lambda mu, Young's modulus C, and Poisson's ratio nu. And now we have bulk modulus K and mu, that sometimes people write as G, the shear modulus. How do we find them using this triaxial experiment? K, as I said up here, is just the ratio of dilation with respect of the equivalent pressure with dilation. So you know the equivalent pressure, that those are the pressures that you are applying to the sample. You can measure the dilation, the total volume change of this sample, and the ratio of those two is the bulk modulus. If you go through this algebra, I won't go through that in detail, but you can see that if you try to relate deviatoric stress to deviatoric strain, you can see that 2 mu is equal to sigma 1 minus sigma 2 divided by epsilon 1 minus epsilon 2. These are all four quantities here are quantities that you measure in that experiment. Okay, so in effect, this triaxial test also allows you to measure properties or for linear hyperelastic isotropic materials. And very briefly, last time I had mentioned this huge set of relationships that's actually a problem 98 in your books that pretty much relates these different possible pairs of material properties. If you have lambda and mu, you can find out C and nu in terms of lambda and mu. You can relate these material parameters with each other and develop new relationships. But I'll point out a few things about these material properties. If you remember from the uniaxial tension test, if I have a material coupon, if I apply a stress sigma 1, I get elongation epsilon 1. And if I apply positive stress, I better have an elongation. If I apply stress, it shouldn't contract, right? That gives me a limit that C always has to be, that Young's modulus is always greater than 0, positive, no surprise there. We also looked at hydrostatic pressure. For hydrostatic pressure, the state of stress is given by P on the diagonals, or negative P on the diagonals, and therefore 1/3 trace of stress, this is the volumetric stress, that would just be minus P, which is what we defined as sigma. And if I have a material, if I apply hydrostatic pressure on it, do you think the volume will be going down, right? It should, if I apply pressure onto it, it shouldn't expand. So in the same way, if dilation is less than 0, meaning contraction, then sigma over k should be less than 0, which is minus p over k should be less than 0, and therefore k, of course, should be greater than 0. That's also not a surprise. But that does bring us to some limits on the Poisson's ratio. So if we look at this relationship, let's see, k is greater than 0. Right. If we look at this relationship, k is equal to c over 3, 3 times 1 minus 2 nu. Now, k is greater than 0, c is greater than 0, the denominator better be greater than 0, right? So, for this to be greater than 0, 1 minus 2 nu has to be greater than 0, which means what's the limit on the value of nu? Nu has to be less than half, right? That's a important property to keep in mind. And the same, there's another limit on the value of nu. You can see that k is equal to lambda plus plus 2 over 3 mu. Lambda, in fact, can be negative, so mu has to be positive. Since mu has to be positive, we'll go back to that table and pick this out. If mu is positive, c is positive, then 1 over 1 plus nu also has to be positive, which immediately means that nu has to be greater than minus 1. So the limits on the Poisson's ratio are minus 1, has to be less than mu, has to be less than half. So Poisson's ratio can only be in this. Can you tell me what a negative Poisson's ratio might mean physically? Right, so Poisson's ratio, as you remember, is contraction in the lateral directions if I apply uniaxial tension test, right? So if I pull on it, you would expect it to contract. There are classes of materials when you pull on it, it expands. So negative Poisson's ratio materials. And then Lamé parameter is also sometimes called the shear modulus, as I just mentioned. And there are these two relationships for those of you who also were in the review session. These two relationships are convenient relationships that allow you to solve common problems at a material point. Given a state of strain, I can use this relationship to find the state of stress. Or given the state of stress, I can use this relationship to find the state of strain. They are both equivalent relationships. Essentially, component by component, if you were to write them out, there would be 9 equations, right? And these are useful relationships that allow you to solve some problems. Let's take a look at some examples. You remember this problem when we were talking about in chapter 3, where we were looking at how can we make sure that deformable bodies are in equilibrium. So I gave you an example of a spherical object that is under uniform hydrostatic pressure, let's say out in space somewhere, so that gravity doesn't play a role or body forces don't play a role. And we said that the stress field is uniform everywhere in the body, minus P times I. And we assumed a deformation map. We said that the body would contract uniformly. So we said, let's assume the deformation map to be alpha times z. And therefore, the displacement map would be phi of z minus z. So alpha z minus z. And which means that the strain would be just the gradient of u. The gradient of u would be alpha minus 1. So this is nothing but alpha minus 1 times z. Maybe I should write it that way. So alpha minus 1 times z, and gradient of u, what would that be equal to? Gradient of u with respect to z. If u is some scalar alpha minus 1 times z, what would be the gradient of z with respect to z? Alpha minus 1 times identity, right? Gradient of z with respect to z is identity tensor. Alpha minus 1 times identity tensor. And since gradient of u turns out to be identity itself is symmetric, so half of grad u plus grad u transpose is nothing but gradient of u in this case, which is this. All right, so let's apply our material model to this to see if I can relate this alpha, that is the amount of or the scaling factor for the contraction, to the applied pressure. That was something that we did not do back in chapter 3 because we didn't know anything about material properties back then. So we'll use this Hooke's model to try to relate that. On the left hand side, we said stress is equal to minus p times I. I'll just write lambda times what is trace of epsilon, if that's my strain, 3 alpha minus 1. Okay, so 3 alpha minus 1 and identity as it is, plus 2 mu epsilon again. I'll just write at alpha minus 1 times identity, and which allows me to relate, since on both sides I have identity tensors, I can relate minus p to the scalar factor here. That would be 3 lambda plus 2 mu alpha minus 1, right? And we know that 3 lambda plus 2 mu is 3 times the bulk modulus. So alpha turns out to be, if I take this to the other side and then add 1, then alpha turns out to be 1 minus p over 3k, which is the scaling factor by which, if I apply pressure P, then alpha would be given by this. That would be the amount by which the radius of that sphere would shrink. And therefore, the map also can be written just as alpha times c, which would be basically the same factor, 1 minus p over 3k. This is alpha times c. So here, what we have done is we have solved a very simple structural mechanics problem. This structural mechanics problem is certainly nowhere close to being as complicated as this, right? There was a body with with some loads, some material properties, and what we wanted to find was displacements, strains, stresses, and everything. And in general, these types of problems are complicated because that stress, strain, everything varies from point to point. But what we have done here is solve a structural mechanics problem for a finite sized body, but what allowed us to solve it was that the stress, strain was uniform. It was the same at every point. So given this black body, given the state of applied tractions as hydrostatic pressure, we were able to find the map that the body would deform in this way, because we know the material, we assume that the material would be behaving with the Hooke's model. So this is the simplest example of a structural mechanics problem. You give me a structure, body forces, loads, boundary conditions, and I can tell you what the map is. Okay, and as hopefully we'll see today, these types of problems we cannot solve in general, because we cannot solve these types of problems for more complicated shapes, or where the stress and the strain profile vary from point to point in a complicated manner. Okay, but we'll take a couple more examples like this. There's So here, this is, I think, one of the problems in your book, that you're given a thin sheet and you're applying tractions 15 psi in this direction, 25 psi in this direction, and material properties of the sheet are given to you: 1000 ksi, Young's modulus, and Poisson's ratio is 0.45. Initial thickness is 0.1 inch. Find the change in thickness after the tractions are applied. That's the problem. Again, this is a mechanics problem. You're given a structure, boundary conditions, material properties, and you're being asked to tell me what the map is, or tell me what the displacement of certain points is. Okay. To solve this problem, what you would need, what would you need to do? How would you go about trying to solve this problem? What are we given and what are we trying to find? Right, so definitely, since we are given boundary tractions, we can set up a stress tensor. And the boundary tractions, if I assume my axes to be along this direction, so let's say this is x1, x2, then my stress tensor in the 1, 1 direction would be 25, in the 2, 2 direction would be 15, in the 3, 3 direction, what would the stress in the 3, 3 direction be? 0. In this particular case, since this is a thin sheet, and actually this is a very important type of state of stress. As the problem says, this is plane stress. That means that all the stress components are in this x1, x2 plane. That anything, there is no stress component out of the plane. That happens for these types of bodies which are thin, like a thin sheet of rubber. If you extend it, the sheet might get thinner, but there won't be any through thickness stress that would develop. Okay, and very shortly we'll see the other type of other common type of two-dimensional state of stress, which is called plane strain, where a sheet of material is constrained from any movement in the third direction. If there is zero displacement in the third direction, there cannot be any strain in that direction. Okay, so my strain tensor has lots of these strain tensor have 9 components. Some of have this index 3 in there, and anything with an index 3 would be 0. That's a plane strain problem, and that happens when a material is restricted from moving in the third dimension. I'll come to that, but let's first talk about this plane stress. For thin sheets of material, if I stretch them, there's 0 through thickness stress. All right, so that's 0, and every other component of stress is also 0. And I think we went through this exercise, I think, in the review session as well, that how do we show whether the other components are 0 or not. So I'll give you maybe a very quick sort of physical argument of why it would be. Let's say I have this sheet and I'm looking at this traction profile on this sheet. If I go to some point and think of this small neighborhood of that point, like a square piece of material, and I'll draw a neighboring square piece of material, another neighboring square pieces of material to that particular piece of material, right? And if you look at those neighborhoods of this material and draw, I'll redraw that. Do you think that, let's say in this direction, this is 1, 1 direction, this is 2, 2 direction, then if I draw the state, or if I draw the tractions on this small piece of material, those tractions would be coming from the neighboring material neighborhoods of material. So do you think if the external tractions are applied like this, there would be traction on we'll try to figure out what types of tractions would be on these remaining faces. So on this face, do you think there will be traction in this direction? Right? The material just to the right of this block, would that be trying to separate out from this material? Which means it would apply traction onto this hashed piece of material. Similarly, material on the left would apply forces in this direction. Material on the top would apply forces in this direction, and the bottom in this direction. Let's see if there's. Do you think that this block, would this block be trying to move up and down with respect to this block of material under this applied state of tractions? Right? I have assuming uniform state of stress everywhere. Would that block that I have marked there, would that be trying to shear against the hatched block that is of my concern? No, right? Which means that there won't be any shearing component of the traction on this face. In the same way, if I capture the block on the top, would that be trying to shear with respect to this hatched block that I've drawn? Again, no. So on all of these four faces, we have tractions that are purely normal tractions, no shear component of the traction, correct? And can we say anything about these particular faces now, knowing that the tractions on these faces are pure normal tractions, no shear component of the traction? These are principal directions. What happens in principal directions? Our stress tensor turns out to be diagonal. So that's why the off-diagonal terms are also are going to be zero. So you kind of have to go through this type of physical reasoning to realize that the stress tensor would be 25, 15, 0 in the third, and zeros everywhere else also. Go ahead, question. Yes, if the stress is not uniform, let's say there are some corner effects or something like that, indeed, we would have not only diagonal components, but in general, we won't be able to solve this problem by this. We would have to solve a complicated set of partial differential equations, which we'll see. All right. So in effect, we are given the state of stress. We have to find the state of strain. So we will use that relationship, the second one of those relationships. So we know pretty much all the properties here. Minus nu is 0.45 divided by C is 1000 KSI. And the one thing that we do have to be careful about here is units. So I'll write everything in PSI, 10 to the power 6 PSI. Trace of S is how much? 40. So that's 40 PSI and times identity. PSI's cancel off. And I think if you calculate that out, you will get minus 1.8, 10 to the minus 5, no units, because of course strain does not have units. Which means what would be the change in thickness in the 3-3 direction? Strain times original length, right? We can apply that only because in the third direction we are assuming that the strain is uniform, right? If the strain was not uniform from point to point, strain times original length is not equal to change in length. Okay, but here we are assuming state of strain to be uniform, so E33 times original length, which would be 0.1, and that just gives me minus 1.8 10 to the minus 6 inches. That's the change in thickness. It becomes thinner by that amount. Okay, make sense? Any questions on this? And these types of problems, as I said, even in the review session, are sort of relatively simple. You assume a uniform state of stress and strain, and you just use those relationships to find. You're given some components of stress or strain, and you have to find the others. Question?
If it is not mentioned that it is a thin sheet or a thick sheet, by the emission thickness, can we say it is a limitation?
No, so this example particularly is for a plane stress type of problem. Plane stress happens when there is no third component of the stress. That typically happens for a thin sheet. So the moment you read the words thin sheet, immediately you should think of plane stress type of problem. Okay. All right. Let's take a look at the other problem that we were talking about, plane strain. Can somebody think of an example of where you might come across a plane strain problem? We want some two-dimensional state of strain. That is, if this is the sheet, then there should be zero displacement in the third direction. So if I have a block of material, if I identify a face or a plane of that material, that face must not have displacements or deformations out of the plane. It might move, but in general we don't want any. It might move as a rigid body in the third direction, but we don't want any relative deformations in the third direction. Can you think of a physical example where that might happen? um, say that again, somebody. Me? What?
It is an assumption I'm being
Beam theory. That's true. In the axial direction, we actually assume that the plane itself is rigid, but the plane adjacent to it, we do allow deformations between those two planes, right? So, beam theory, in that sense, wouldn't fit this particular state of strain. One example, indeed, is like a dam, a cross section of a dam. So if you think of, let's say I have a wall, a rectangular wall that I've put up here, and this wall is a long wall between two rigid supports, let's say two mountains. So if I construct a big concrete dam in between two mountains, and if you look at the cross section of that dam, there's a lot of material to the left and to the right of that cross section, which is going to be extremely hard to move. So that's an example where you would take that cross section, and that cross section would not have any movement in the 3-3 direction. That's an example of a plane strain problem. Okay. And this is basically what it would look like. If you think of that cross section, it's fixed between two immovable plates, two rigid plates. And then you're applying tractions on the boundary of that cross section, which means that if you press it in the lateral directions, it would try to expand in the third direction, correct? Since it is not allowed to expand in the third directions, do you think that the stress would be zero in the third directions? No, the strain is zero, but the stress is not zero in the third direction. Whereas for the plane stress problem, the stress is zero in the 3-3 direction, but the strain is not zero in the 3-3 direction. Plane strain, the opposite thing happens. Strain is zero, but stress is not zero. So let's see what this problem is asking for. Material properties are given: initial thickness of 0.3 inches, find stress after tractions are applied, and find out of plane tractions, which is basically the 3-3 component of this stress, and find the ratio of change in volume versus original volume, something you've actually looked at for your homework problem as well. So what do you think would be the state of stress for this particular body? Again, I'll pick 1 and 2 in these directions. So state of stress in the 1-1 direction, minus 35. In the 2-2, minus 15. And since I don't know the third component, I'll just write S33. And again, we'll use that relationship that relates strain to stress. So, and if we look at the 3-3 component, we know that that has to be equal to 0. Minus nu would be 0.2 divided by 10 to the 6 psi. Trace of stress would be minus 50 S33, so S33 minus 50 psi That goes away. And plus 1.2 divided by 10 to the 6 and S33 also in PSI, so that will go away. And we know that that state of strain in the third direction has to be 0. That immediately gives me an equation to calculate S33, and you will find that S33 turns out to be 10 psi, negative 10 psi. What does negative 10 mean, by the way? Compression, right? Positive tractions and positive components of stress mean tension positive is the convention in mechanics generally. By the same notion, then you can go back, plug this in here, calculate E11 to be minus 0.03 10 to the minus 3, E22. The other two diagonal components of that would be these values. And what about change in volume? Delta V over V is obtained approximately as trace of epsilon, right? And trace of epsilon would just be the minus 0.03 and minus 0.006. Just add them together. E33 is already 0, so we get that's the trace of epsilon, which means that that the relative or the relative change in volume of this sheet of material would be 0.0036%. Okay, and that's very similar to the problem that you solved for the homework as well. Any particular questions on this? Go ahead, Kevin.
The change of a certain plane, can I calculate it just like the change of volume, like for a plane in XY, and its change is equal to epsilon 11 plus epsilon 22?
I'm not sure if are you talking about change in area of the face?
Yes.
Yeah, so in this particular case, the final area would be rectangular. If you find the length and the breadth, that would give you the final area as well. But I think maybe you're referring to how the solution found the face area of the face. Is that what you're referring to?
Yes, just like the homework 2, problem 2.
Mm-hmm.
It's asking for the change of.
Right. So, I mean, yeah, this, keep in mind, this itself is an approximation.
Yeah.
Now, you could find the volume and find, I think in that case, you needed to, maybe the final height was known, and you needed to divide volume by the height to find the cross-section area. Or you could do E11 and E22. Your results might be very slightly different, which is because this is an approximation. Okay, go ahead, Spencer.
Why would it ask for the change in volume to be divided by volume?
Say it again.
Why would it ask for the change in volume to be the change in volume divided by volume? Just find delta V?
Oh, if you just want to find delta V?
Well, it says change in volume, so why would it just
I think it says find the ratio of change in volume to original volume. Sorry.
So, it says change in volume.
Right, right. Oh, I guess you're right. So I should write it as ratio of. So this is indeed ratio of the change of volume to the original volume, delta V over V. Okay, question?
We were discussing about the plane strain problem.
Mm-hmm.
That example. Isn't you consider a cross section somewhere in, let's say, x2, x3 direction, right? In the plane direction also, it will be a plane strain problem. It will be hanging in the direction where actually the water pressure is at.
Okay, yeah. So let's say this was our dam cross section, and we have dam on the left and the right of it, and maybe on this side I have water pressure building up like a triangular profile. So typically, what would happen would be this would be like a tall wall which would deflect, just like a beam. It would deflect like as if this was a cantilevered column subjected to a distributed load, a distributed triangular load, and therefore it would deflect. So in plane, it would have deformations, but not out of plane.
I was saying when we consider this cross section,
Uh-huh. I see. So you're saying that in this direction, if
even that could be considered as a rigid body
um,
rotation or motion, and then even that should be considered as a
so
straight problem.
typically that is not the case. So maybe I'll write that here, try to draw that here. For simplicity, let's just take a cantilever wall. Right, and let's say this end is fixed, this end is fixed, and if my axes are to be consistent with the plane strain assumptions that we are using, then 3 would be in this direction, 1 pointing up and 2 pointing out of the plane. Right? So plane 1, 2, in the 1, 2 plane, so 1 times 2, yeah, 3. So in the 1, 2 plane, my cross section looks like this, which is what we just talked about was a plane strain cross section. Do you agree? Now what you are saying is that cross section in the 1, 3 plane should also be considered as plane strain. Now this typically does not happen because you can think of let's say um, um, what do you mean? So if I build up water pressure on this side of the beam, then maybe what it would look like would be let's say something like this, right? And therefore it would try to bend something like this. Maybe I'll draw that as well. Try to bend something like this. The through thickness changes here are typically possible, right? It is moving in the 2 direction. For it to be a plane strain problem in the 1, 3 plane, there cannot be any movement in the 2 direction. Do you agree? For it to be a plane strain problem in the 1, 3 direction, there cannot be any movement in the 2 direction. But clearly, there is movement in the 2 direction. So you cannot have that as a plane strain. Okay. All right. So I think I don't have a lot of time, but I don't need a lot of time to go through this last topic of hyperelasticity. This is again an aside, essentially, for those of you who might end up working with large deformation mechanics. Um, so we've talked about this very restrictive class of materials, linear isotropic hyperelastic materials with 2 material constants. And as I mentioned, that is very restrictive. That usually holds for material for deformations where deformations are not large, very small deformations, typical deformations that we see in our structures, buildings, and bridges. But not all mechanical components or structures actually sometimes have large deformations. So under those conditions, you do have to build up material models that would be able to capture the behavior of the material under those large deformation cases. So the process of developing those material models for large deformation problems is also exactly the same as what we did for the small deformation case. We will write the work done on a particular piece of material and integrate it over the volume of the body to find the total work done on it. And that would be stored as strain energy within that body. So what I'm writing here is, for example, the total, the incremental work done at a particular material point in the body. Let's say I have a material point that undergoes displacement U or du, and the traction dot with du integrated over the surface area of that patch. That gives me the work done on that small patch. Okay. Similarly, body force times displacement. Force times displacement is work done, right? That's exactly what these 2 terms are capturing. And by writing traction as stress times normal, then rearranging that because stress is symmetric, using the divergence theorem, I can write that instead of a surface area term as a body term, divergence of S times du. And if I go through some algebra, you can see that this incremental work done turns out to be du dot div S plus b, which is 0 because of equilibrium, and um, plus stress double dot, hopefully you remember double dot, Sij times gradient of V ij. What we get is a term that gives me very similar to what we had for the small deformation. We just had epsilon dot here. Now, what we get for the deformation is S double dot with L. L, hopefully you remember from kinematics of finite deformations with time dependent deformations. What was L? L was velocity gradient, meaning du over dt is velocity, right? Displacement time derivative is velocity. Gradient of velocity with respect to the current configuration or to the with the deformed configuration x, that was L. That's the velocity gradient. And so that's the total work done by external tractions and body forces as a body undergoes some large deformation in time. And again, through a bunch of algebra, you can convert that dv in the deformed configuration to original configuration dv. You can rearrange all of that to come up with Js and L replaced by F dot F inverse, and you can show that we get Js F inverse transpose here. That's the first Euler-Kirchhoff stress times double dot with F dot. And if you do another substitution, you can show it that it's a second Euler-Kirchhoff stress tensor double dot with E dot. This E was the Green Lagrange strain. So essentially, if you look at this term, this was the term that we had even for the if deformations are small, this L just boils down to E dot. That was the term when we had when we were talking about small deformations. Cauchy stress is work conjugate, because this is essentially energy. When you take Cauchy stress, you have to choose linearized strain. That would be work conjugate to give me a work type term. If you choose first Euler-Kirchhoff, you have to choose F. So P is work conjugate to F, and second Euler-Kirchhoff is work conjugate to the Green Lagrange strain E. These are all just equivalent definitions um, of the work done on a body and the energy stored at a point in the body. And the idea is still exactly the same, that if you give me a strain energy density function, I give you a few different examples here. If you give me a strain energy density function, I can take derivatives of that function to find either Cauchy stress or first Euler-Kirchhoff stress or second Euler-Kirchhoff stress. Okay. In the exact same way that for your homework problem 2, I gave you a strain energy density function, took derivatives, you found Cauchy stress. Right? So that this type of material behavior, people actually do experiments to try to develop these types of functions. But essentially, the idea is very similar to small deformation cases also. I won't go through the details of this, and then finally, very quick note about this class of materials. There are these class of materials which are perfectly incompressible or near incompressible. You may know that water is treated as incompressible. Rubber sometimes is treated as incompressible material, where and for incompressible materials, local volume change is 0, which means local volume change is 0, and which means the determinant of F, which was the ratio of final volume divided by original volume, turns out to be 1. This happens to be a bit of a problem for these class of materials, for incompressible materials, for which people have to handle them in a different way to try to try to relate stress and strain. But I think I won't go into too much detail about this topic, and we'll stop here. Next time, we'll come back and start this chapter 5, where we'll actually solve uh, more interesting problems in mechanics rather than just uniform state of stress, plane strain, plane state, or and look at what problems can be solved. Okay. All right. So I'll see you on Wednesday.